Hi, y'all. It's Mrs. Blasky. I'm going to try and make this as short and sweet as I can to give an introduction to equilibrium. And so to start this off, I got to tell you about another chemistry lie that we've all been telling you. When we've been talking about chemical reactions, we've always said that reactions just happen. Your reactants turn into products, and then you're done. That doesn't always happen. Sometimes it does, but not all the time. So many times reactions will start to proceed. Those reactants will start to form products. And then it will look to us like the reaction has stopped, either with a lot of products formed or maybe just a little bit of products formed. But what's really happening, and if we could look super close and see what those molecules are doing very, very closely at a very, very small scale, we would see that not only are the reactant particles bumping into each other using that collision theory that we learned last chapter to form our products, but that also some of the product molecules are colliding with each other and going back and forming reactants. And so what we call this phenomenon is chemical equilibrium. When we, from the macroscopic view, from us looking at a beaker, it looks like the reaction has stopped. But on the microscopic scale, on the molecule level scale, the reaction is still occurring. We still have reactants forming products, but we have products forming reactants at the exact same rate of reaction. And so that's when we say that a chemical system is in equilibrium. So it looks like everything is done, but on a very small scale, there is still a lot changing, a lot of things going back and forth. And so we can represent this equilibrium in lots of different ways. And so we're going to talk about all the different ways we can represent equilibrium. So one way to represent equilibrium is with a graph. When we graph concentration versus time. Now notice, this is not going to be like kinetics. We're not going to be talking about how fast reactions are going necessarily. We're not going to be talking about orders of reactions. We're just going to be saying, hey, we started off with this concentration and now we have this concentration. Are we at equilibrium or not? So we can track the concentrations of our reactants. We can see that our reactants started with concentrations and then reduced that concentration over time. We can see our product, ammonia, increased concentration. And then at some point, those concentrations stopped changing. So past that point, this is in chemical equilibrium. This system is not changing concentrations anymore on a macroscopic viewpoint, but on a microscopic viewpoint, those reactants are still forming products. Those products are still forming reactants. So there's a bunch of sort of questions and example problems here, just making sure that you can follow along with what the data is telling you so that we can identify when things are in equilibrium and when things are not in equilibrium. So there's a bunch of those. We need to be able to see it both in terms of graphical representations and in terms of particle representations, and we will practice those in class. A second way that we can represent equilibrium and determine whether something is at equilibrium or not is something called an equilibrium expression. To write an equilibrium expression. Now I know that we've had kinetics on our brain for so long, we're going to sort of throw all those rules out the window and start over brand new fresh when we're talking about equilibrium. When we have a system and we do not know if it is in equilibrium or not, we are going to write an equilibrium expression in terms of Q. Capital letter Q, we call this our reaction quotient. So anytime we either know we are not at equilibrium or we are not sure if we are at equilibrium or not, we write this in terms of Q. Our equilibrium quotient is a ratio of reactants underneath, products on top. It's a quotient because we're dividing. And each of those reactants or products is raised to a power of the coefficient in the balanced chemical equation. Now, we can write a reaction quotient in terms of concentrations, where we use those square brackets, or we can write a reaction quotient in terms of pressures. If all of the reactants and products are gases, we can write it in terms of pressures. It's going to work out the same way. Big difference, and this is something important that will get you counted off on questions. If you're talking about concentration, about molarity, you need to use square brackets. If you're talking about pressure, you need to use parentheses, the rounded brackets. If we know we are exactly at equilibrium, then we use that exact same mathematical representation of products over reactants raised to the powers of their coefficients. But if we know we are at equilibrium, then we use a value called K, or the equilibrium constant. This is not lowercase k from kinetics. This is a capital letter K for kinetic, or for equilibrium constant. Now I'm saying it too. This equilibrium constant does not, we are not concerned about the units on it, but we are going to use the value of this number to tell us more about what's going on in the reaction. So if we have a situation where we can solve for our Q, and we know what the equilibrium constant for that reaction should be, we can compare the value of Q to K to know what's going to happen to that reaction. So if my Q value is larger than the K value that I've know to be true for that reaction, that means I have more products and less reactants than I need to be at equilibrium. So that means that my reaction is not at equilibrium currently. It means that I need to form more reactants, have less products in order to come to equilibrium. So lots of times we will use the term shift when we talk about this. We'll say that that reaction needs to shift to the left to form more reactants to come to equilibrium. If we calculate our Q value and we find that our Q value is smaller than our K value, that means we have too many reactants and not enough products to be at equilibrium. So again, that means our overall reaction is going to shift to the right to form more products, use up some reactants to come to equilibrium. If Q and K are equal to each other, then we are already at equilibrium, and that reaction does not need to shift one direction or the other in order to achieve equilibrium. So for example, let's see how this works out. So example number 17 here says, for the synthesis of ammonia at 500 degrees Celsius, the equilibrium constant is 6.0 times 10 to the negative 2. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. So first thing I need to know is I need to know my balanced equation. This equation was used farther up on the page. So nitrogen plus hydrogen makes ammonia. We need to balance that. That needs to be a 2. That needs to be a 3. So my Q expression, my equilibrium expression, since I don't know if I'm at equilibrium or not, I got to use Q, is going to be products over reactants. This is all in terms of concentration, so I know I'm going to use square brackets. So I've got the concentration of NH3 is my product. It's got a coefficient of 2, so I'm going to have a 2 there. My reactants go on the denominator. I've got N2, which has got coefficient 1, so it's raised to the power of 1. And then H2, which has got a coefficient of 3, so that one is cubed. So now I plug my concentration values that I have right now into this equation so that I can figure out what's going on. NH3 has a concentration of 1 times 10 to the negative 3 molar. That's going to be squared. Hydrogen is 2 times 10 to the negative 3 molar. That's to the first power. And then, oops, I did that backwards. That's H. That's going to be cubed. And then nitrogen is 1.0 times 10 to the negative 5. That one's going to be the first power because nitrogen is raised to the first power. There we go. All right, so we plug that into a calculator. When you're doing these calculations, you're going to have to get real familiar with your parentheses on your calculator and your EE or EXP button, because a lot of this is going to be in scientific notation. So when I do the math on this, I got 1.25 times 10 to the 7th. So comparing that to my K, my Q is way bigger than my K. If that is way bigger, it means I've got too much product, not enough reactant. So I'm going to shift back towards the left to make more reactant. So we're talking about this situation here where my Q is way bigger than my K. So again, we sort of need to be able to do that in terms of math and in terms of explaining what's going on. Some other things that we need to know about writing out our equilibrium constant and our equilibrium expression. So our equilibrium expression, just to make sure that these all make sense, equilibrium expression is the equation, the Q equals products over reactants or K equals products over reactants. Your equilibrium constant is actually that value for K. And again, your equilibrium or your reaction quotient is Q. That's when we don't know if we're at equilibrium or not. So a couple important things to know about that. When we write out our equilibrium expression, pure solids and pure liquids do not go in our equilibrium expression. Basically because a pure solid or a pure liquid has infinity concentration. And so changing that concentration is not going to have any effect on equilibrium because it's infinity minus a little bit is still going to be infinity. So only aqueous solutions and gases are going to show up in our equilibrium expressions. If we know information about our equilibrium constant, it lets us know several different things about what's going to happen in that reaction. Knowing the value for K will tell us, is this reaction likely to happen or not? Is it likely to form a lot of products? Is it likely to form a little products? Now, a reaction can be very likely to form products, but happen very slowly. And so equilibrium has no correlation to kinetics. Just because we're going to make a lot of product does not necessarily mean that it's going to happen fastly. Quickly. Oh my goodness. Just like what we did, figuring out our Q value, if we know what our K value should be, we know what concentrations we're starting with, we can say, hey, is this a good condition, a good set of conditions in order to help this reaction happen or not? And then we can also sort of know where equilibrium lies in terms of the reactants and the products for that particular reaction under those particular conditions, under that temperature, that pressure, all that sort of things. If our K value is much larger than 1, remember that our equilibrium expression is always products over reactants. So to get that K greater than 1, that means that we have to have a lot of products and not a whole lot of reactants. So if our K is greater than 1, that means that we say our equilibrium lies towards those products, or that we make a lot of products and use up most of our reactants. A K smaller than 1 means that that forward reaction is not occurring very often, so that we are creating much fewer products and maintaining much more of our reactants. Very rarely do we get a K of exactly 1. It's possible, but it's not special in any particular way. Because again, we have squareds and cubes and exponents in there, so it doesn't necessarily mean anything specific about that particular reaction. We can use an initial equilibrium constant K for a balanced equation, and we can modify that balanced equation, which means we're also going to have to modify our K value for that. So basically, whatever we do to the balanced equation, we also need to do to the K value. So if we wanted to talk about the reversed reaction, K is going to be inverted. So if I have the reaction of A making B, now notice that that's got a double-sided arrow because we're at equilibrium, and it has a certain K value. If I want to talk about the reverse reaction of B forming A, then because we're talking about the reverse, we're switching the products and reactants in that equilibrium expression. My K, or my equilibrium constant, is going to be inverted. It's going to be 1 over K instead. If we change the coefficients, if we triple the reaction, if we quadruple the reaction, we're also, this is actually wrong. Change this in your packet. K is going to change exponentially. So if the coefficients are doubled, K is going to be squared If it's tripled, that means K is going to be raised to the third power, because that's what we're doing. Those coefficients become the exponents in our equilibrium expression. So K is going to be affected exponentially by that change in coefficient. And we'll see that in an example in just a second. If we have multiple stepwise reactions that we end up adding together, like we had in mechanisms, we can multiply those Ks for all of those steps together to get the K for that overall reaction. So let's see this in real life. Let's see how this works. So we've got here in example 32, we've got our original equation, PCl5 mixed PCl3 and Cl2. So if I want to write out my K expression for this, notice that this is in terms of pressures now, and so we need to use our round parentheses. So this would be the pressure of PCl3 times the pressure of Cl2 over the pressure of PCl5. Now, none of those have coefficients other than 1, so it's going to stay that way. And so its value for K is just K. Now, if we notice in the second equation, all of my reactants and products have been raised to coefficients of 3. So my K expression is going to change. My K is going to be the pressure of PCl3 raised to the third power, the pressure of Cl2 also raised to the third power, over the pressure of PCl5 raised to the third power. So how is that going to change my K? The K for this reaction is going to be the cubed of our original K. In this third reaction, we can see that it's the same as the original reaction, only reversed. We have the reactants in the product's place and vice versa. So my K is going to be basically the upside down version of my original K. So this would be the pressure of PCl5 on top, the pressure of PCl3, and the pressure of Cl2. So because it is switched around, my K is going to be 1 over that original K. So however we modify that balanced reaction is how we modify our K. So we'll be practicing all of this in class, talking about what language do we need to use when we do this, how do we represent this in graphs, how do we represent it mathematically, just to sort of get a handle on talking about these different types of reactions where they are coming to equilibrium rather than just saying all of our reactants stop and turn into all of our products. I will see y'all in class, and I'll talk to you later. Bye.